Hello everyone, and welcome to tonight's stream. And let me just get set up here. We are doing 3.8. There we go. All right, so we're doing Book of Proof, Richard Hammock, 3rd edition. You can download it in the description of the video. It's in the Creative Commons. I have a physical copy. It's a very nice book. And I'm going to do the reading, and then I guess depending on what time it is, I'm going to do the questions, or maybe I'll break it up into 2 parts. I have been sick, so my ability to turn these out has been somewhat limited. All right, let's see where we're at. Okay. Okay, this is page 96, Counting Multisets. All right, and then cool. All right. Counting multisets. If you have in your pocket 4 pennies, 2 nickels, and a dime, and 2 quarters, you might be tempted to regard this collection as a set. All right, let's just do that. So we have. So then we have 4 pennies, 2 nickels, 1 dime, 2 quarters. But this is not a valid model of your collection of change because a set cannot have repeated elements. To overcome this difficulty, we make a new construction called a multiset. A multiset is like a set except the elements can be repeated. We will use square brackets instead of braces to denote multisets. So we are just going to change the bracket type. That's a multiset. There we go. Repetition of elements is allowed in a multiset. A multiset is a hybrid of a set and a list, and a multiset elements can be repeated, but order does not matter. So yeah, we can write it in whatever. So for instance, we can go 1, 1, 2, 1, and this would be the same as 2, 1, 1, 1. Okay. So given a multiset, its cardinality A is the number of elements it has, including repetition. So the cardinality here is 9, okay? Okay, now, the multiplicity of an element of X containing A, of an element X in set A, is the number of times that X appears in set A. So in other words, the multiplicity of our 1s is 4, multiplicity of our 25s, our quarters, is 2. Okay, 10 has a multiplicity of 1. Notice that that every set can be regarded as a multiset for which each element has a multiplicity of 1. In that sense, we could think of as an empty set as the multiset that has no elements. Okay, so an empty set, which is equivalent to, these two are the same symbol. Listen, an empty set, both are the same symbols. This is also how you would write it, like this. A multiset with no elements. To illustrate the idea of multisets, consider the multisets of cardinality 2 that can be made from symbols A, B, C, D. So we have our usual A, B, C, D. A minute. So this is our regular type of set that we've been using, regular set notation with elements. This is multiset notation below now. We have A, repetitions allowed, order doesn't matter. A, B, so notice I'm not going to write BA, because AB and BA repetition is the same, or the order will not matter, so I can't repeat it. In other words, look, if the order was important, I wouldn't be able to do this, BA, and because I can do that for organizing them, we only do it once. AD, okay, and then we have B. Let's see here, B, comma. Now what we're doing here is, this is a cardinality of 2, so we're doing doubletons. BC, BD. In other words, we're making multi-set. These are the doubletons only. And then we have C, CD, comma, D. Okay. And then it also shows us what a multi-set of 3 elements would look like. And it ranges from AAA to DDD. Though the set X, ABCD, has no subsets of cardinality 5, there are many multisets of cardinality 5 made from these elements, including AAAAA, or AABCD, and so on. Exactly how do we get there? This is the first question about multisets that we can tackle. Given a finite set X, how many cardinality K multisets can be made from X? Let's start by counting the cardinality 5 multisets made from symbol of X equals ABCD. So now we have a 4 element set, and we're going to create 5 cardinality or 5 element multisets out of it. So it's going to be interesting. Our approach will lead to a general formula. We know we can write such a multisets with letters in alphabetical order. Tweaking the notation slightly, we can write such a multisets with bars separating the symbols. Notice that if a symbol does not appear in the multiset, we can write the bar that would have separated it from others. Okay? Okay, let's do this. A, B, C, D. So because of repetitions allowed, we can have 2 A's, and then we're going to say okay. This is encoding to star. This is called stars and bars. Okay. So anytime there is the same type, they can be by the same. The stars could be together. Anytime there's a different type of element, you have to separate it by a bar. So here we have 1A separated by a bar, 2 B's. Then we have separated by a bar from the C, separated by a bar from the D. Stars and bars. Okay. All right, so now we have okay. Wait a minute. A C C. So we're not using a b in this version, okay? What's interesting here is that we are still... Now notice how in this case is the first one where we are starting with 1 bar followed by 2 stars followed by... Hold on. No, wait a minute. This is 2 stars, bar, AA. Now we're putting 2 bars here. And then CC and D. That's interesting. So, oh, right. Okay. The reason why the 2 bars are side by side is because there's no B. They separate where the B would have been. That's why there's 2 bars instead of 1. So it retains the, it continues to encode the form of the A, B, C, D. Even though the B disappears, it encodes an empty spot for it. At least that's what I'm understanding it to be. Okay, so we have... Okay, so here we have a... There we go. So, no A. We're just going to start with a bar then, because there would have been an A, followed by 2 stars for B's, followed by stars to separate the B's and the C's. There's no C, so we close that with a bar, separating from the D's. Okay, yeah, that works. Okay. A. Okay, so then we're gonna have star, 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 star. Then we have A from the B, there's no B. B from the C, there's no C. C from the D, there's no D. Okay? Yep, okay. Except I drew that in the wrong area. Let's see. A. Okay, that's fine. There we go. Okay. This suggests that we can encode multisets as lists made from 2 symbols, stars and a bar, with star for each element of the multiset as follows. Star for each A, star for each B, star, and so forth. For examples, see the right-hand column of the table. Any such encoding is a list made from 5 stars and 3 bars, so the list has a total of 8 entries. How many such lists are there? We can form such a list by choosing 3 of 8 positions for the bars and filling the remainder 3 positions with stars. Therefore, all the possible ways we can arrange with a 5-element multiset separated by 3 bars is going to be 8 to choose 3. So 8, not A. 8 to choose 3, right? All of these have 1, 2, 3, 4, 5, 6, 7, 8. 8 elements, and we're choosing the placement of the bars. So 3. Everything else gets filled in. And then, so then that case, we're going to be 8 factorial over 3 factorial, 5 factorial. Okay? So, or let me just do this correct. 3 factorial times 8 minus 3 factorial. I jumped a spot. So we have 8 times 7 times 6 times 5 factorial over 3 factorial. That's a 6. And then we have 5 factorial. So we can scratch the factorials, the 5 factorials, and we'll scratch the 6. So that's 35 different ways. Okay? And so 3 factorial is 6, so I immediately converted that to 6, and then I scratched the 6 from the top. I would have still gotten the same number. You can multiply 8 times 7 times 6, and then divide that by 6, or you can multiply 8 factorial out to multiply that 3 factorial by 5 factorial and divide the 8 factorial by that. But the thing with factorials, at least like these lower level factorials that we're doing, you could do it by hand pretty quickly. And honestly, doing it by hand, you get a better appreciation of how it works instead of just like punching them in the calculator. So I personally prefer doing it by hand. Okay. Hold on. Okay, everything was correct about what I said, but it's 56, not 35. I can't do math. I'm sorry. I'm not good at math. Anyway, it's 56. Yeah. 8 times 7 is 56. But yeah, right. Everything else stands. Okay, 56 different ways we could encode our 5 cardinality multisets. That, yeah. Okay, good. So in other words, let me see here. The way you could think about it. Okay. For any size of, let's say 1, 2, 3, 4, 5, 6, right? All you got to do is figure out how to separate them all. You don't have to put any beginning, but you don't want any two elements touching each other, right? The two exterior elements can touch the ether on the outside, whatever you want to think of it. But fundamentally, we have 1, 2, 3, 4, 5. You're only going to need, why is that 4 bars? Hang on a minute. Oh, that's 5. Right. Because we were working with, hold on. Let me figure this out. Oh, right. We're working with 4 elements, A, B, C, and D. That only needs 3, right? Because while we were putting them as 5, we were using repetition. But fundamentally, it's, and what happens with us, if we have 4 of a type, then any one of those types, we only need 3 separators. So for instance, if we have 5 element set, but it's 2 of a type, A, B, B, right? There's 2 of a type, then we just need the 1 separator between them. Now, so that's really the trick to understanding here. Because we had 4 of a type, we need only 3 separators, even though we were using 5 elements, but there was only 4 of a type. So that's how you kind of know. You need to know how many types you have. We have 4, so that means we need 3 separators. But you also need to know how many total elements, including the repetition, which was 5. So then that's how we got the 8 choose 3. 3 represents the separators of the types, and the total separators, the bars, plus the number of stars, and the stars count, including repetition, each of the elements in the set. You add it together, and that's how you get the 8 choose 3, basically. In this case, my bottom example here, we have, it's going to be, I guess it's just going to be 6 choose 1. That should be it, really. Yeah. Okay. So, to figure that part out. Anyway, let's keep rolling along. If you wanted to count the cardinality 3 multisets made from X, then the same reasoning would apply, but with only 3 stars instead of 5. We'd be counting length 6 lists with 3 stars and 3 bars. There are 6 choose 3, so 20. So there are 20 cardinality multisets made from the A, B, C, D. So in other words, what they're saying here, let's see here, we had, do cardinality 3. So this was a cardinality 5 multisets. We could have dropped 2 out of it, and then that would have been cardinality 3. Yeah, basically that's what they're getting at here. Now let's keep going here. In general, given a set X, X1, X2, X3 to the Xn, any cardinality K multiset made from its element can be encoded in a star and bar list. 1 star for each X subnumber, X sub 1, X sub 2, and so forth. Such a list of K stars, 1 for each element of multiset, and n-1 separating bars, a bar between each of the n grouping of stars. Therefore, its length is k plus n-1. We can make such a list by selecting n-1 list positions out of k plus n-1 positions for the bars, inserting the stars in the leftover positions. Therefore, here's another good formula here. We have k plus n-1, choose k. Okay. So then, yeah, we had, k plus n. Right, so that would have been, so continuing here, let me just see something real quick here. This works out because any cardinality K multiset made from the n elements of set X can be encoded in a star and bar list of k plus n-1, having a star for each subnumber. Okay, and for example, the number of 2-element multisets that could be made from a 4-element set X, let's see here, X, we're going to say our set A, B, C, D. Okay, and then we're going to say 2k is equal to 2. So that's going to be 2 plus 4 minus 1, choose 2. Okay, so that's going to be 5, choose 2, that's 10. Okay. Yeah, that's right. And I just know the top 5 choose 2 is 10. I know at the top of my head. So, yeah. I'm gonna drink real quick. Okay. Right. Now, we have set A, B, C, D. If we wanted to make a 5-element K, right? So, well, let's see. Let's do that. If we were to do, if n would have been 5 plus k would have been 4, I guess. 5-element plus 4. Hang on. So we had a multiset of, for each element of the multiset. So if we had a 5-element of the multiset, and k is represents there are k. Oh, it's n. It's not k on the bottom. It's n-1. Oh, I know it is. It is. This formula also is equivalent to k plus n-1 over n-1. Okay, the two are equivalencies. Okay, cool. So then, if it's a 5-element set, I guess it would have to be if we say there's a 5-element set, and the equivalent k would have to be k is equal to n-1. So that would be 4, and then we would need 4 plus 4 minus 1, 5 over 4. Is that right? I don't know. I'm just trying to work some of this out as previous examples. See, I can't seem to get a 5 choose 3 out of this thing. That's what I'm trying to create here. But let's just keep rolling on and see what happens here. I'm trying to make the formula work for the previous example, but it's fine. We'll get to that. From elements of an n element set is k plus n minus 1, which is equal to k over n minus 1. Okay. So if it's a 4-element multi-set, it's still, oh, I see, because the right, as we were said previously, a K only refers to a separator of different type of elements. If it's multiple repeating elements, so let's say we're going to say A, B, C, D, A, B, C, D. There's going to be only 3, and then that's going to be, all right, so now our N, so our K is equal to 3, our N is equal to 5. So now we are getting 3 plus 5 minus 1 over 3. That's not what K is. I don't know. I guess I'll have to figure this out as we go along here. Okay, okay, this agrees with our counting of them on page 96. Does it, though? That's what I'm trying to get. I don't see how that accounts for our counting on the previous page. Now, the way it worked out made perfect sense to me because, okay, we had 8. We go 1, 2, 3, 4, 5, 6, 7, 8. 8 different things. And then we're choosing 3 positions for the bars. Then we're going to say choose 3. So that makes total sense to me. How to get this to work with this formula is the part that's not jiving with me here. I can't get that to work out. Okay, let's see here. Okay, well, we'll figure it out. The number of 3-element multisets that can be made from elements of set X, 3-element multisets, okay? And so we're going to give it a 4-element set. We're going to say 3-element multisets. So now we're going to say K is equal to 3. And we have 4 elements. So let's just use our formula, see what happens here. We're going to say 3 plus 4, n is equal to 4, minus 1 over 3. So that is going to be 6. 6, choose 3. Okay. So yeah. And that's going to be 6 factorial over 3 factorial. 3 factorial, which is going to be 6 times 5 times 4 times 3 factorial over 3 factorial. We're going to call that 6 times 3 factorial. So that's going to be 20. 20 different ways. Now, if we were to say, take our ABCD, and we're going to say 3-element multisets, so I guess that would need 3 bars. All right, 1, 2, 3, 4, So that should be 7 choose 3, not 6 choose 3. Okay. All right, let's see here. The number of 3-element multisets that can be made from elements of set X, A, B, C, D, is 6 choose 3. Now, if we look on page 96, and how many 3-element multisets do we have here? So they did list out 20. So that agrees with that. I guess we just have to stick to the formula because the answer is 6 choose 3. So instead of counting the stars and bars, I'm not sure why that worked in the first one though. But okay, well, I guess then that's what we're gonna do. We're gonna go with the 6 choose 3. There's some rule where it probably is because this is the there are no repetitions right now in the one that we've been doing here. So this rule, I guess, applies to a non-repeating one. I don't know. We'll have to see it because these are each unique elements, A, B, C, and D. Whereas this one was a 5 elements made out of a 4-element set. So basically we had a repetition going on there, and that's probably what's changing with this thing. Anyway, that's the only thing observation that I can make here. The number of 1-element multisets made from set X is, okay, so A, B, C, D. So we're going to say 1 element n is equal to 4. Using our formula, k plus n minus 1 over k. So that's going to be 4 plus, 1 plus 4 minus 1 over 1. So that's going to be 4 choose 1. Okay, and that should be 12, I believe. No, wait a minute. Sorry, that's 4. Right. So 4 choose 0, or I'd say n choose 0 is always going to be 1. And n choose 1 is always going to be n. So that's a quick thing that you can remember that. Okay. Okay, right. So, and then, so if we have, last one here is n is equal to 4, k is equal to 0. And what do we got here? We have 0 plus 4 minus 1 over 0. So that's going to be 3 choose 0. And remember what I said, anytime you have n choose 0, it doesn't matter that the number is going to be 3, it's still going to be just 1. And that is only the empty set. So yeah, this rule, this formula holds for that. So that's fine. That's good. All right. A bag contains 20 identical 20 red marbles, okay. I'm going to say marbles. 20 red, 20 green, and 20 blue. Okay. And then you grab, and you reach in and you grab 20. Okay. We're going to say choose 20. So that's going to be 40. Okay. So there are many possible outcomes. You can have 11 reds, 4 greens, 5 blues, or all 20 reds altogether. So each outcome can be thought of as a 20-element multiset made up from 3-element set X. So we're going to say the set. We're going to say RGB. And then, yeah. So then the total number of outcomes is going to be here. So what is n then? So k, we're choosing, so this is equivalent to k. And then we have to figure out what n is. N represents okay, right. N is equal to 3. So then, by our formula, we have k plus n minus 1 over k. So that's going to be here 20 plus 3 minus 1 over 20. And that comes out to 22, choose 20. Okay, and that's going to be 22 factorial over 20 factorial over 22 minus 20 factorial. And that comes out to 22 times 21 times 20 factorial over 20 factorial times 2 factorial. We're going to call that 2. I'm going to scratch the 20 factorials. We're going to scratch the 2, make that 11. And that's going to be, let's see here, 231. Yeah, because 21 times 10 is 220 plus 21 is 231. Cool. All right. So yeah, there are 231 possible outcomes. Nice. Rather than remembering the formula, in fact, 3.7, it's probably best to work out a new stars and bars model as needed. This is because it is often easy to see how a particular problem can be modeled with stars and bars, and once they have been set up, the formula falls in automatically. Okay, so we could also solve this with stars and bars. Right, so then we have 20 options, and then we're just going to say, we're going to say R, let's say G and B, and then, so yeah, we have 2 bars, and then the only difference is that there are 20 stars, so we're going to say 20 stars, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So then 20 stars, again, the spread could be whatever, right? They can choose more stars for one, less stars for the other, but just to get an idea. But we have a 22, and we have to choose 20. There. So that works out. Perfect. Our next example involves counting the number of non-negative integer solutions to w plus x plus y plus z. By a non-negative integer solution to the equation, we mean an assignment of non-negative integers to the variables that makes the equation true. For example, let's do it. So then we have w plus x plus y plus z is equal to 20, and then we only need containing integers. Okay. All right. So all the integers, so basically all, hang on a minute. Let's do it this way. Let me be a little bit more clear. Okay, so we're going to say we're going to say w, x, y, z all are going to be, there are going to be are greater than 0, and comma contain integers, something like that. Okay, so sorry, or equal to 0. We can use 0. All right. So W can be 20. The rest would have to be 0, for example. But we can't have any negative for any of them. Okay. We can model a solution with stars and bars. Okay, so let's do that. So we're going to say W, X, Y, Z. So we need 3 stars, and we have 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20. So by my count, that's going to be 23. 23. Choose 20, right? Yeah, choose 20. But my understanding. Wait a minute. We can make such a... Actually, the number of ways is 23, choose 3. So, right. K is equal to 3. So then we have n, wait a minute, k plus n minus 1 over k. And that comes out to k is going to be here 3. And so we have 20, 21. But wouldn't that be 22? Choose 3 if we use the formula. Okay, why is this not working? Let me see here. Okay. Here we go. There are 20 plus 4 minus 1 over 20. Oh, right. So you can do it what I did earlier, saying 23 choose 3 and 23 choose 20 is the same stuff. It'll give you the same result. So where did it? Why is this? Okay, for another approach, model suggests W plus X plus Y plus Z is equal to 20, made up of elements W, X, Y, Z. For example, corresponds to W, X, Y, Z. By fact 7.3, it's 20 plus 4 minus 1. Where are they getting the 4 from? Fact 3.7. K plus N minus 1. The N is 20, the K is 3. Where are they getting 4 from? I mean, you need it to be 23. That much is true. But they're not very good at explaining this part. See, this is the thing with math books, especially as you get up higher. They assume something's to be true, and I mean, it makes sense to them, but it does not make sense to me. Because I can make it work in the sense that I can go, okay, there are 20 n's, and I can go the 20 and plus 3, so we can go 23, choose 20, right? We can do that. That makes sense to me. Also, the alternative, I could also do 23, choose 3. That totally makes sense to me. And by the way, let's just do that number so we can prove that the two are equivalent. So we have 23 times 22 times 21 times 20 factorial over 20 factorial times 6 times 3 factorial. Scratch these. Okay, and then what we have here is this is going to be 6. This is going to be 2 times 3. And then we're going to make this 7. And this is going to be 11. So that's going to be 77 times 23. Okay. Yep, and that comes out to 1771. Okay. 1771. Okay. Now, here we have 23. Choose 3. Okay. So then we're going to go with well, it's the same thing. We're going to 23 times 22 times 21 times 20 factorial over 3 factorial times 20 minus 3 factorial, which comes out, 23 minus 3 factorial, which is 20 factorial. And we're going to say this is 2 times 3, in other words, or 6. So we scratch this, makes this 7, make this 11. There we go. So now we have 77 times 23, 1771. 1771. Okay, so that makes sense. Okay. WXYZ are 20 element multisets made from elements WXYZ. Yeah, I don't know why they're turning the 3 into a 4. The K, as it's defined, is simply the number of bars. Let me see here. Such a list has K stars for 1 for each element of the multiset and n minus 1 bars. Oh, okay. Oh! Okay. Now I get it. I've been redoing it backwards. These are the stars. Wait a minute. But that doesn't make sense either. So that's fine. If that's the case, so this is n. So that's going to be 4 for a number of elements, minus 1. And then how did we end up with 20 for the stars? Okay, so we're counting stars and bars. Okay, I think I'm starting to get it. I was counting the 3 as the K. The 3 represents stars, and the 4 represents elements. So now I'm starting to... This is why, you have to struggle with this to get it sometimes. But if you just blow through it, it'll come back and bite you somewhere. You really have to take your time and understand it. Even if you have to go around in circles till you get it. So, we're going to... Let's do this one more time. K is equal to stars. And we have n is equal to elements. So, and then the bars, we're not counting the bars at the moment. So if we did that, we're counting, so we're choosing 20. So that's going to be 20 plus number of elements, 4, minus 1. And then it's going to be choose K, which should be 20. Right. So that makes sense, which is 23, choose 20. Right. Now, so this is, okay, there's two methods they're trying to teach us. That's why I kept getting confused. One does not count the bars. And this is the stars and elements. This is going to be stars plus bars, okay? The stars plus bars, we count the number of stars. We're going to have, so we're going to say stars plus bars over, this is going to be bars. So that's going to be 20 plus 3 over 3. So that's 23 over 3. A little different. You could think of it, notice that it doesn't use the formula, but you get to the same result. If you have 23 choose 3 or 23 choose 20, the result's still going to be the same. Okay. So, wow, that was a doozy, but good. I'm glad we did that. Okay. Now, next, by the way, we're on page 100, so that's a big deal. We're on page 100. Okay. Example 3.21. You have a list of W, X, Y, Z integers with the property with W is greater than or equal to 0, less than or equal to X, less than or equal to Y, less than or equal to Z, less than or equal to 10. Okay. And how many such lists can we make? Okay. So we have 10 stars. Let's see if I can figure this out. 10 stars. We have 4 elements. 1 limit. Does 0 count as an element here? W, X, Y, Z. Does 0... W has to be greater than 0. So if we're just counting stars and how many bars can we have? Let's see. W, X, Y, Z. So if we just do stars and bars, that's going to be 13, choose 3. At least that's what I'm getting. Let me see here. No, wait a minute. But that's not what they're having here. We encode the list as 10 stars and 4 bars. Why 4 bars, though? There's only 4 elements here. Shouldn't it be 3 bars? W is the number of stars to the left of the first bar. X is the number of stars to the left of the second bar. Maybe it's the conditional of it. But we had the conditional in last time. Okay. What is 13 choose 3? Actually, no. Even if you get the same answer, even if that would probably not work. So let's see here. I guess the conditional is going to be 4. So W is greater than 3. That means there could be a number. So So let's see here. Let's see, 2, 3, 4, 5. Does that work? That's too much. There's a very limitedness. Set that in here. Let's see, 1, 2, 3, 4. That's gonna be 10. But you could have equal to. All right. 2, 3, 3, 3. So that should work. But that's 11. Let's try 2, 2, 3, 3. There we go. That works. But that means that anyway, they're saying there's a let's see here. We can encode a list with 10 stars. Yeah, I agree with that. And 4 bars, where W is the number of stars to the left of the first bar, and X is the number of stars to the left of the second bar. Okay. But I mean, if they're saying basically it's this, and I don't understand why you need to do that. But basically that's going to be 10. Choose 4. Or is it, sorry, 14, choose 4. Choose 4. So that's adding up the stars and the bars. Gets us 14. All right. Times 13 times 12 times 11. Times 10 factorial over 4 factorial, that's 24, times 10 factorial, scratch that, scratch this is 2, this is 7, okay, 77 times 13, 1001. Okay. All right. Okay. Well, it takes some getting used to figuring out how to apply the stars and bar method. We will examine one more type of multi-set problem. To motivate it, consider the permutations of the letters of the word book. B-O-O-K. First instance, there are 4 letters. We should get 4 factorial, or 24 permutations. But this is not quite right because 2 of the letters are identical. We could interchange the 2 O's, but still have the same permutation. To get a grip on the problem, let's make one of the letters lowercase. Okay, so we have the list book in 24 permutations, all right? The columns in the oval, we're on page 101, by the way, correspond to the same permutation of the letters of book as indicated in the row below the oval. Thus, there are actually 4 factorial over 2. That's 24, choose 2, or divided by 2, which is 12 permutations of the letters book. So the columns in the oval represent the same permutation of the letters book as indicated in the row below. That's because there's 2 O's. So essentially, you take the 24 and then you divide it by 2. The permutations. So then we end up with 12 permutations. This is actually a problem about multisets. And the letters book form book, and we are determined there are 12 permutations of the multiset. This is actually a problem about the letters book form a multiset book, B-O-O-K. We have determined that there are 12 permutations of this multiset. Okay? For another motivational example, consider the permutations of the letters of the word banana. There are 2 N's and 3 A's. Though some of the letters look identical, think of them as distinct physical objects that we could permute into different orderings. So, yeah. Well, whatever. It's 1, 2, 3, 4, 5, 6. And it's just going to be 6 factorial, right? So 5 factorial is 120 times 6, that should be 720? Yeah, 720. So in other words, we have the letters B, we have A1, BAN1, A2, BAN, N2, and then we're going to say A3. So A1, A2, A3, N1, N2, and a B. So that's 6. So we have 6. And since we're doing with how many different ways, it's going to be times 5, times 4, times 2, times 1, which is 6 factorial. Look at that. Anyway, it's not practical to write all of them, but we can get a sense of the problem. Yeah. Okay. But, I mean, that just makes sense, right? In this case, we want to know how many unique ways we can combine them. Even though the A's repeat, this is A sub 1, A sub 2, A sub 3, N sub 1, N sub 2. So think of them as distinct types. So these are non-fungible A's or non-fungible N's, meaning that the item or number, the subscript associated with it, makes it unique. So A1 is not equal to A2. So, and that's not equal to A sub 3. So, there. Okay. I hope that makes sense. Supposing a multiset A has n elements with multiplicities, P1, P2, P sub 2, P sub k. The total number of n permutations of A is n factorial divided by the number of subscripts. So, oh, wait, hang on a minute. 12 of them correspond to particular permutations of banana. Oh, I hadn't finished the question, by the way. So n's could be permuted in 2 different ways, n factorial 2 ways, and a's in 3 factorial ways. So, what we need to do is we have 6 factorial over the number of a's, 3 factorial, and the number of n's, 2 factorial. So that comes out to 720 over 6 times 2, which is going to be divided by 720 over 12, and that's going to be 60. Okay. Total number of permutations of A. So basically, if we were to treat each of them as distinct, like this, if we were to do this, then it would be equal to 720. However, if we were to say that while distinct, they are fungible, you could swap one for the other. Then it would be this. Basically, that's what it's getting at. Okay. Let's do Mississippi. I S S I S S I S S I P P I. So we have M. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 factorial, and then we have 1 factorial for the M, and then this is going to be I, we're going to have 4 factorial for the i's. And then for the s, it's going to be 4 factorial for the s. And for the p, 2 factorial. 2 factorials for the p. Okay? And let's figure this out. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial over 4 factorial. Let's see. Well, forget about the 1 factorial. 4 factorial 2. Okay, and 1. So let's drop the 4 factorial. Let's decompose the 4 factorial into 24. And does that do me any good? Let's do this. We're going to say 3 times 3 times 4. And then we're going to get rid of this. We'll drop the 9. And now we have a 4, and we'll get rid of the 4 and the 2. We'll get rid of the 8. So that means we've just cleared out all our numbers. In the denominator, we have 11 times 10 times 7 times 6 times 5. Okay, so that's going to be... Alright, so... That's going to be 30 times 7, it's 210, times 110. So that's going to be 23100. I think that's right. It looks right. 23,100. Wait a minute. My math was wrong though, but let's see here. The permutations I wrote out was correct, but it's 34,650. Let me figure out where I screwed up here. Okay, 23. Alright, so let's just do it this way, fine. 11 times 10 times, here, I'm just going to do 11 factorial. Okay, and we're going to divide that by 4 factorial, divided by 2. Okay, so actually it is 34,650. Okay, so yeah, the math, I made a mistake in the numbering, but what I did do correctly was that it was this. This was the correct answer. So that was done correctly. Okay, here's a multiset. Let's do this multiset. All right. 1, 1, 1, 1, 5, 5, 10, 25, 25. Number of permutations of the multiset. We're going to say 1, 2, 3, 4, 5, 7, 8, 9. So we're going to say 9 factorial, and then we have 4 factorial, 2 factorial, 1 factorial, 2 factorial. So, which is equal to 9 times 8 times 7 times 6 times 5 times 4 factorial over 4 factorial. And then we're going to say 2 times 1 times 2. Okay, we're going to scratch that. So let's just take out the 2's, take out the 8. We'll call that 2. All right, so then we have 9 times 2 times 7 times 6 times 5. Okay, and that's 3780. All right. Okay, that wasn't too terrible. All right. Yeah, so let's see how I do on the Q&A part. We're going to roll right into it now. Oh, wow, we're almost there. Okay. Okay. Here we go. How many 10-element multisets? 10. From the symbols 1, 2, 3, 4. There are 4 symbols, and we have 10. So that's going to be, if we do stars and bars, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hang on a minute. 1, 2, 3, 4, 10. Okay, so we have 10 and we have 3. So we have 13, choose 10. Also, 13, choose 3 is another way to think about it. And if we wanted to get the 13, choose 3, it would gonna be k is equal to 10, n is equal to 4. 1, 2, 3, 4. 4 elements. So that would be k plus n minus 1. Choose k. N minus 1. Choose k. And that comes out to 10 plus 4 minus 1. Choose 10. Which comes out to 13, choose 10, which is the same. All right, let's do that. All right, so we have 13 factorial over 10 factorial with 13 minus 10 factorial. So that's going to be 13 times 12 times 11 times 10 factorial. And then over 10 factorial times 3 factorial. Scratch 10 factorials. 3 factorial is a 6. And 6, we're going to scratch that, take the 12 out, make that a 2. So it's 13 times 2, which is 26 times 11. We'll call this 26. All right, 26 times 11. It is 286. All right, that's what I'm getting. Let's find out. All right. Yep, 286. All right, next question. Answers in the back of the book, so you can download the book and you'll know if I'm right or wrong before I do. And keep in mind, I get plenty of questions wrong, so don't assume that just because I'm doing something, I know what I'm doing. Okay. You have $1 in pennies, okay? There's 100, okay? You have $1 in pennies, $1 in nickels, and okay, 20. $1 in dimes. Okay. And $1 in quarters. All right. You give a friend 4 coins. All right. How many ways can this be done? All right. So this is our n. This is equal to our n. And this is our k. All right. So then we're going to say n is going to be 100 plus, it's going to be, we're going to use our formula, k plus n minus 1, choose k. All right, so that's going to be 100, 34, that's 134 minus 1, which is equal to 133, and it's, which is equal to 4, 133, choose 4. Okay? All right. Right, let's write that out. So we have 133, 132, 130, 130, 129 factorial over 4 factorial, 129 factorial. Get rid of that. All right. So that's going to be, let's multiply those out real quick. 133, 132, 131, 130. Okay, and then we're going to divide that by 6. All right. Make sure I did this right. All right, I'm getting this right here. 297,080. 49,829,780. That's what I'm getting. All right. Let me check my. Okay, let's find out. Oh, no. That's wrong. It's because this is not 6. This is 24. Okay, so that's wrong number. I just caught that right before I was about to check for the answer. Let's do that one more time. 133 times 132 times 131 times 133 times. And also, that's a 1, not a 3, 131. Okay, 133, 132, 131, 130. And then we're going to divide that by 24. Okay. 1, 2, 4, 7, 4, 4, 5. 12,457,445 is what I'm getting. All right, let's find out. Right. Wait a minute. You have $1 in pennies, $1 in nickels, $1 in dimes, $1 in quarters. You give 4 coins to a friend. How many ways can this be done? In giving your friend 4 coins, you're giving your friend 4-element multi-set made from elements. Oh. I did something different here. I did the number of the Mississippi version. Basically, I counted the number of permutations if they were how many different combinations you can do. This isn't quite right. This is money is it's fungible, meaning that 1 quarter is equal to any other quarter. So that's not correct. In this case, there is going to be here. Let's do this one more time. So let's do this. We have so the K we're choosing 4. A minute. There are 4 different types. Plus 4 minus 1, choose 4. I think it's 7 choose 4. 7 choose 4 I think is 35 at the top of my head here. Let's try this. 7 factorial over 4 factorial times 7 minus 4 factorial, which is equal to 7 times 6 times 5 times 4 factorial over 4 factorial, 3 factorial, which is 6. Scratch the 6, scratch that. 5 times 7 is 35. Okay. So yeah, if it was non-fungible, meaning that if every quarter was different, and we wanted to find out all the different ways of arranging all the different quarters, then this would have been it. But because money is fungible, the answer is this one, 35. Yeah, so it's 35. Okay. All right. Bag contains 20 identical red balls, okay? 20 red. And then we have 20 blue. 20 green. 1 white. And then you choose 15. Choose 15. How many different outcomes are possible? Okay. So that's going to be K. K is equal to 15. N is equal to 4. So we're doing K plus N minus 1 over K. All right. So we are getting 19 choose 15. Okay. Wait a minute. K plus N is 19, but it's minus 1. Right? K plus N. So it's 18 choose 15. All right. 18 times 17 times 16 times 15 factorial over 15 factorial with 3 factorial. Scratch that. That's 6. Scratch the 6. That becomes 8. That becomes 3. Okay. Scratch this. 18. That becomes 6. So it's 48 times 17. Okay, I'm getting 816. Okay, so we have 4, 4n, and then we have the fact that there are, we're choosing 15. Does it matter, though, the fact that there's 20 and we're choosing 15 out of them? Should it be 61 choose 15 or something like that? I don't know. But remember, it didn't matter in the previous one because of the fungibility. So because they're all fungible, it shouldn't matter. We're not worried about all the different arrangements between them. We're choosing 15 out of here, and there are 4 different ones. 4 different types. I think that's right. Let me see here. Choose, first we count the number of outcomes that don't have a white ball. Okay, wait, why are we doing that? That's, okay, why are we doing that? 20 red balls, 20 blue, 20 green, and 1 white ball. You're at 15. First, we count the number of outcomes that don't have a white ball. Modeling with stars and bars. All right, well, let's just do that. So if we were just to say the white ball doesn't appear, so that should be 17, choose 15. Yeah, that would be 17, choose 15. Okay, so no white. 17, choose 15. Okay. Because again, it's going to be K, which is 15, and is going to be, in this case, we are going with 3. So it's 15 plus 3 minus 1 over 15. So that's 17, choose 15. Okay, and let's do that. So that's 17 times 16 times 15 factorial over 15 factorial times 2 factorial. Scratch that. So that's going to be 8. 17 times 8. So that's 136. Okay, so if we did that, now we count the outcomes that do have the white ball. All right, so if we did that, the way they count with the white ball is that we take our, what is it, 17, choose 15. I had, wait a minute here. 15, 16, 17. Oh. It should have been, when I wrote 18, choose 15, I forgot the minus 1. It should have been 17, choose 15. This should have been 17, choose 15. Let's take this out of here. So, now, no white. Now we're going to say with the white. So we're going to, again, let's start by saying we have 15 plus 3 minus 1 over 15. So that's going to come out to 17, choose 15. And then minus white. So that's 1, choose 1. So that comes out to 16, choose 14. So that comes out to 16 times 15 times 14 factorial over 14 factorial, 2 factorial. Okay, that's 8 times 15. So that's 120. All right, I'm guessing we just add the 2 possibilities. Right, so 136 plus 120, it is 256. So, why did we do it this way, though? When we did the quarters, we had $1 in pennies, which is 100 pennies, $1 in nickels, $1 in dimes, $1 in quarters. I guess because technically in those cases you could have actually given your friend all 4 coins of any denomination. Because you're giving your friend 4 coins, so technically it could have been all 4 quarters. In this case, you couldn't do one where it was the white would have completely dominated it. Its weight wasn't significant enough. So because of that, we had to figure out what the situation was when white was the 1. The odd man out. Okay, so that makes sense. Okay, 7. So we have 20 balls. Wait a minute. 20 balls. And then 5 different boxes. 1, 2, 3, 4, 5. How many ways can you place? Isn't that 20 choose 5? Seems like 20 choose 5. Yeah, let's do that. 20 choose 5. Okay, so that's going to be 20 factorial over 5 factorial over 20 minus 5 factorial times 19, 18, 17, 16, 15 factorial over 5 factorial times 15 factorial. Scratch that. This is 120. Scratch this. That's going to be 6. Scratch the 6. That's 3. So 19 times 3 times 17 times 16. Alright, I'm getting 15504. I think. I don't know. Let's find out. No, that's not correct. 5 different boxes. So 2, 3, 4. So here's how you want to take the approach. So we have 20 balls. And we have 5 boxes. So let's just go 1, 2, 3, 4. So it's going to be 4. And then stars and bars. So that's going to be 24 choose 20, I guess. Should be 24 choose 20. 24 choose 20. I think, let's try that. 24 times 23 times 21 times 20 factorial over 20 factorial 4 factorial. Okay, and yeah, 10, 6, 2, 6. Okay. 10, 6, 2, 6. That's the way. Okay. This was the correct answer. All right. Let's keep rolling along. Yeah, this stuff's hard. Definitely, it's not easy. Take a long time to really get used to doing these. All right. 9. Okay, so we have 50 pennies. 50 pennies. 50 nickels. 50. So they have equal weight. 50 dimes, 50 quarters. You grab 30 coins, so you choose 30. So we have n is equal to 4 because they're all fungible. K is equal to 30, so we have 30 plus 4 minus 1 over 30. So that comes out to 33. Choose 30. All right, so let's try that. 33 times 32 times 30 times 31 times 30 factorial over 30 factorial times 3 factorial. All right. And we're going to scratch the 30 factorial. 3 factorial is 6. Let's just make this 3 times 2. All right, and then we're going to make this 11 and make this, what is this, 19? Wait a minute, no, 16. 11 times 16 times 31. $54, $56. Okay. Again, there's no guarantee I'm gonna get this right. Let me try this. How many different outcomes are possible? Well, assuming that money is fungible, which it is, then it should be 54, 56, I would think. Yeah. It's 33 choose 30, 54, 56 outcomes. Good. All right. 11. How many integer solutions does the equation w plus x plus y plus z equals to 100 have if w is greater than or equal to 7, x is greater than or equal to 0, y is greater than or equal to 0, and z is greater than or equal to 0. Okay, well, there should be, I guess, 4 bars. Last time we did this, there was 4 bars. So let's just go with 4 bars. Let me see what the example we did with. Okay, so we can model it. Non-negative solutions W, X, Y, Z have. So it used 3 bars here. For W, X, Y, Z. However, there's a second one where they used 4 bars. And I need to understand what the difference was in them. The condition was that how many non-negative integer solutions? So W plus X plus Y plus Z lists with list W, X, Y, Z of integers with the property that each entry is an integer between 0 and 10. The entries are ordered from smallest to largest. And the integers are ordered from smallest to largest. We can encode such lists as, let's see here, so 2, X starts at 2, 3, 4, 5, 6, 7, 8. W, X, Y, Z. So the way this works, I think I'm starting to get it. Let's just draw like if X, Y, and Z are 0, so we can have X has 0 stars, Y has 0 stars, Z has 0 stars, and W has 100 stars. So we can do that. what if we could also do this? If W for X has 100 stars, but does it need to be? Well, all I know is that it's going to be... Let me look at the question again. How many integer solutions does the equation wxyz have if there's a condition on it? Well, you know what? I'm going to say if there's a condition, there's 4 bars. And if it's 4 bars, so we're going to say 4, and then it adds up to 100. So it's 4 choose 100. Yeah, 20. So we're going to say 4 bars, 100 stars. So we're going to say 104 choose 100. 104 choose 100. So 104 times 103 times 102 times 1 times 100 factorial over 100 factorial times 4 factorial. Okay, so that's 24. Now I'm just going to multiply those out and divide it by 24 afterwards. Okay, 104 times 2 times 101. We're going to divide that by 24. Okay, I think that's the answer. 4 million, 4.5 million. Wait a minute. Let's see here. This is how many integer solutions? 11. Okay, what? You're saying it's 97, choose 3. Okay, how many integer solutions does the equation have? Oh, okay. I get it. Let's do this one more time. So we know, wait a minute. 97. Wait a minute. Okay. 11 is, it's not 7, it's 4. It's greater than or equal to 4. So realistically, we're not choosing 100 balls. So we have, it would be 1, 2, 3. This is W plus we have to pick 96 spots, right? So 1 plus 96. And then, and now we're going to say there's going to be 3 bars between them. So really, So 1 plus 96, so it's going to be 97. Choose 3. Like that. Stars and bars. So this counts as 1 star. Then we have 96 stars. Well, by 1 in the sense that, remember how we did bars? How it was, we would have here, like that. But because these could only be the W's and they're locked in somewhere, that counts as 1. So we're adding that together. So it's 97, choose 3. And 97 times 96 times. So 97 factorial over 3 factorial times 94 factorial, which is 97 times 96 times 95 times 94 factorial, 94 factorial, 3 factorial. Okay, so 97 times 96, 5 divided by 6. Wait a minute. Here we go. I wrote 95 twice. That was the problem. Here we go. I think. Yeah, here we go. So it's 147440. 147440. Okay. All right. I mean, a lot of these are tricky, and I have really struggled getting them right. But, I do understand them, when they explain it. And that's really what it's about. Like, you need at least to be able to, like, kind of work it out. And this isn't even, like, the last time I'm going to be going through all this stuff because I'm preparing to retake this class. So that's coming up in about a month now. So I'm pretty far ahead in this book. I'm feeling pretty confident in retaking this class now for the 3rd time. But the reason I didn't finish it before was that I would focus on work and then I would fall behind with the schoolwork. So anyways, now I want to go in and pass with flying colors and a deep understanding. That's what I want. It's really about having the understanding. How many length 6 lists? Length 6 lists. We made from the symbols A, B, C, D, E, F, G. And rep allowed. And the list is in alphabetical order. So, in other words, so you can run all A's, for instance, or you can go all A's and a B on the end of it, but you can't do like BBA, that kind of situation. All right, let's see how to work this part out. So, well, let's see here. If we were to do, it's kind of a hard question to really break this down. How will this map out? If I did all A's, See, like I did A, 1, okay. So this has 6 options, right? This also has 6. 6. But not really, because I can go A. If I go B here, I can't go back here. So it seems like it drops. So if I go A, that's 1, that's fine. What if I go A, B, 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 B? So if I go with B, I can go B through 6. It sounds like just like a factorial, really. I would think that this would probably be something like 6 factorial. I would say it's 6 times 5 times 4 times 3 times 2 times 1. It kind of like reverses the repetition being allowed, being in alphabetical order. Kind of takes that away, I think. The other way to think about it would be, yeah, no. Let's do it this way. A, B, C, D, E, F, G, 2, 3, 4, 5, 6, A, B, C, D, E. Stars and bars, right? We can have all A's for the stars, 1, 2, 3, 4, 5, 6 A's, and then it'll be 0 for the subsequent lettering. So we keep our order. It's stars and bars. That's what it looks like to me. So then we have the length is 6, and then we have 1, 2, 3, 4, 5, 6 bars. And 2, 3, 4, 5. Wait a minute. G is 7, right? 2, 3, 4, 5, 6. Yeah, G is 7. Length 6 lists with 7 elements. Okay. So we have. So we're gonna say 6 stars plus 6 bars. So that's gonna be 12. Choose 6. I think that's how we should do it. Okay, so that's going to be 12 times 11 times 10 times 9 times 8, 7 times 6 factorial over 6 factorial, 6 factorial, scratch 6 factorial. 6 is going to be 6 times 5 times 4 times 3 times 2. And we're going to get rid of the 12. And then we're going to get rid of the 3, we're going to get rid of the 9, we're going to turn that into a 3. And we're going to take the 5, get rid of the 10, turn that into a 2. And take the 4, and we're going to get rid of the 8, turn that into a 2. So now we have 2 times 2 times 3 is 8. Wait a minute, no, sorry, 12. So we have 12 times 11, and that's 131 times 7. 131 times 7. I think that's right. Sorry, 132. That's right, that was wrong. Times 7, 924. I think the answer is 924. 13. Yes, it is 924. Look at that. Look at that. Yeah, I did stars and bars. They did the K, which is 6 for the list, and the number of elements, which is 7. So alternatively, you can do this. So I did stars and bars. You can go with K plus n minus 1. Choose K, whereas K is equal to length, which was equal to 6, and n is equal to elements, which was equal to 7. So that is alternative. We can go 6 plus 7 minus 1 over 6, which is 12, choose 6. Okay, so I got that right. That's good. All right. How many permutations are letters in the word Tennessee? I've been in Tennessee. It's a great state. Yeah. Great music. All right. Let's do Tennessee. Okay. Permutations are there of the letters. So counting permutations is n factorial over p1 factorial times p2 factorial times pn factorial. Okay? Right. So we have t is, we have 1 factorial. E, we have E1, E2, E3, E4. So we have 4 factorial. And N, we have N1, N2. That's 2 factorial. S1, S2. That's 2 factorial. So that should be 9 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 factorial over 2 factorial, 2 factorial, 1 factorial, and 4 factorial. All right, so 9 times 8 times 7 times 6 times 5 times 4 factorial over 1 times 2 times 2 times 4 factorial. Scratch that. Let's get rid of our 2's, get rid of the 8, make it a 2. All right. So that's 9 times 2 times 7 times 6 times 5. All right, 3780. 3780. Okay, let's take a look. Yeah, 3780. That's good. All right. Okay, that was Tennessee. Let's try 17. You roll a dice 6 times, okay? Times 6. Rolls. Okay. How many possible are outcomes with there being 2 1s, 3 5s, and 1 6? Okay, so 2. Okay. Let's go with 1 1. This is what we want. 5 5 5 6. All right, let's do stars and bars. We're allocating stars in this case. So we have so we have 1 2 3 4 5 6. And we're going to say we have 2 stars in the 1. They have 3 stars in the 5 and 1 star in the 6. So we're going to have 6 stars, 2, 3, 4, 5 bars. So we're going to say 11, choose 6. All right, and that's going to be 11 times 10 times 9 times 8 times 7 times 6 factorial over 6 factorial, 5 factorial. Scratch that. This is 120. So let's see here. Let's scratch the 10. It gives us 12. 12 is going to be 3 times 4. So 3 times 4. We'll get rid of the 4, make the 8 into a 2. Get rid of the 3, make the 9 into a 3. So we have 11 times 3 times 2 times 7. So that's going to be 66 times 7. So 66 times 7. 462. 462 is what I'm getting. All right. Okay. No, that's wrong. The approach should have been the permutations one. So if you do the permutations, it's gonna be 2 factorial, 3 factorial, and 1 factorial out of 6 factorial. So 2 factorial, 3 factorial. All right, let's do that. Then it's going to be 6 times 5 times 4 times 3 factorial over 2 times 3 factorial. Scratch that. 6 times 5 is 30 times 2 is 60. And that is the answer they gave us. It's 60. Okay, so yeah, just it's permutations basically for that question. All right. Okay, in how many ways can you place 15 identical balls into 20 different boxes? Okay, if each ball can hold at most one, if each box can hold one ball. So that, okay, I got this. I think I got this. So we have 15 balls. And then we have 20 different boxes. We can hold 1 per ball per box. So really, if we think about it that way, I guess the 15 is going to be gone. This is, I think this ties back into the 97 choose 3. So if the 15 gets taken up, so the question becomes something like this. I guess it's stars and bars, but we can only give 1 star per bar, so shouldn't that like discount it? I think that maybe we subtract the 15 from the 20 and then just do the 5 factorial, because then that just shows you all the different ways you can rearrange between the spaces. I don't know. So let me think about this. What would it be? What's the equivalent here? Yeah, I think it's just 5 factorial. It seems kind of small. That would be 120. And how many ways can you place 15 identical balls in 20 different boxes? So you get 20 boxes used up, and then you just leave with 5 empty boxes. And then you just have to figure out how many ways can you rearrange the empty boxes, right? Alternatively, we can try stars and bars, but the stars and bars implies that you can have all the stars between two bars. I do think that it's either stars and bars or the 5 factorial. So if this was, well, hey, let's try this with a small number. Say we have 4 boxes and we have 3 things. So we can go 2, 3, 4. So we can go ball, ball, ball. Ball, empty. Ball, 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 empty. Ball, ball. There, ball, empty. Here, ball. Say ball, 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 ball. Does that account for all the different ways? So it seems like I did that. I can't think of any other arrangements where I can do it. They're identical balls. So I demonstrated, so it's 4 choose 1. I did there. All right. What if we had, say we had 3 and 5, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we get a 1, 2, 1, 1, 2, 1, 1, 2, 1. And we're going to say 1, 2. And then we're going to say da, da, da. And then space, da, space, da, da, da. So that's going to be, it's going to be a small number. If I did that, what was that? I did 5 choose 3. I think that's what I did. So 5 choose 3 is going to be times 4 times 3 factorial over 3 factorial times 2 factorial. That's 10. 2, 3, 4, 5, 6. There should be 4 more iterations, I think. Oh, right. 4, 5. There's one in the center, 7. I don't have to think of all of them. I just have to get a feel for what the pattern does. I'm betting it's 5 choose 3. I'm almost guaranteed that that's going to be the answer here. 2 balls here. 3 balls here. 3 balls. And then there's another pattern I could see here. Da, space, da. So yeah, there's not that many we can do. 1, 2, 3, 4, 5, 6, 7, 8. I'm assuming it's going to be 10. So it's 5 choose 3, really. And the way I got around that is I said the number of balls is identical. So the number of spaces we have is how many? We have 20 different boxes. So we're going to say 20 choose 15. Let's do that. It's 20 times 19, 18, 17, 16, 15 factorial over 15 factorial and 5 factorial. Scratch 15 factorial. Scratch that, that's 120. Scratch the 20, that becomes a 6. And then scratch the 6, the 18 becomes a 3. Okay, let's try this. 19 times 3 times 17 times 16. Okay, ooh, that's a big number. 15504. All right, Yeah, I think that's the answer. We're gonna find out. Yes, that is the answer. It was 20, choose 15. Good. See, like something I talked about in a previous video. This is a tool that wasn't really taught to me, but I kind of figured out on my own, and it's a very useful tool. So you have a equation which you don't quite know what the way to approach it is. So you build a toy model, right? So I built a couple of toy models to get a feel for how it's gonna work as it grows, and based on that, I was able to infer the formula to use. Anyway, it's a thing that I use, and if it works for you, oh, that's great. But yeah, it's just one of my quirks. All right. Anyway, how many numbers between 10 and 99 contain one or more digits 3, 4, and 8, and no others? Okay, let's see. We have 10,000 and 9,999. Okay, between them. Contain one or more digits of 3, 4, and 8. No others. No. All right. How about between, I don't know, let's say, how about between, I don't know, 10 and 20? Between 10 and 20. Contain 3, 4, and 8. Let's do this. But no others. So then we have none, actually. One or more of these digits, but no others. So about between 10 and 99. Probably a little bit more sense. Well, the lowest I can have here is going to be 34. We have 38. Contain one or more of the digits 34, 348, but no others. Okay, 34, 38, 33, 33, 34, 38. Then we go on to 43, 44, 48. And then it's going to be 83, 84, 88. So there's 9 here. How? So that's the answer for that my toy model here. I can think of no other ways I can get these numbers, but no others. Contain one or more of the digits 3, 4, so 88, 84, 83. And presumably, I can probably just add a couple of zeros on there. To go up, but what's the? How do I get 9? That's okay. Ooh, I don't know. So it's choose 3. So I did choose 3. 3 different numbers I can choose, right? K is equal to 3. K is equal to 3. And no. N is equal to 3. K is equal to 2. Let's try that. Is it 4 choose 2? n plus k plus n minus 1 over k. So that's going to be 5 choose 2, which equals to 10. There should be 10. And no, hold on. It should be 10. The feeling is right, but we have to subtract one number, and I gotta prove why. Or I have to find that number that exists. It does feel like a 5 choose 2 though. Come on, you could figure this out. 33, 34, 38. And maybe it's the empty set? K is choose 2. In this case, so we could have, so the range works. Why is it 9? What can give me a 9? 3 choose, 4 choose. I know. I'm gonna look at the binomial theorem and see if I can get a 9 in it. I doubt it. No, there's no 9s. Yeah. Unless you're adding 2 permutations. We could do, yeah, we could do that. We can do a, 4 choose 2 plus 3 choose 1. And that's 6 plus 3. That's a possibility if I wanted to do that. 4 choose 2. 3 choose 1. Or I can just subtract 1 to get that number. Or, alright, let me think about this. 3, 4, and 8, but no other. 5 choose 2 is 10. 33, 34, 38. 43, 44, 48. 83, 84, 88. That's 9. Another possibility, let me try this. What if it was, we can have 3 factorial for, how many 3s can we have? 3's can appear twice. 2 factorial times 2 factorial times 2 factorial. We can try doing it that way. That's going to be 8. 8 choose what will give us 9. 8, hang on a minute. 8 would have to be 88. That might work. That might actually work. If we went with 99 minus 10, it's going to be 89. But that's going to be 11. At least, I don't know. I don't see how this thing is going to work out. All the possible numbers are going to be 89 numbers. And so there's 89 numbers, 89 possible numbers, right? 89. And we know that we can do 9 of those. Yeah, that's closer to like, if it was 09, then that should be 10 possibles. I don't know. All right, well, where I'm going to go with it, I'm just going to say that the answer is going to be so we can have 1, 2, we can have 5, choose. K can be 5 instead of 2 now. All right, so then we're going to say stars and bars probably in this case. What if we did stars and bars in the first one? What if we did this? We can go. So how many bars? We can have 1 bar, right? We can have 1 bar. We can have, actually no. 3, 4, and 8. Right? And then we just have the bars. So it would be 2 bars and 3 items, because then we can go choose 2 stars, 2 bars. Two stars, 2 bars. Okay, so that's going to be 4 choose 2. 4 choose 2. Okay, so that's 12. That should be 4 choose 2. That's 12. But that's on if we can have a third one being 0. I think that's what's going on here. I guess if all 3 were 0, that doesn't make sense though. I mean, they would be 12 if all 3 can be zeros. Or more specifically, if we can have 0, 3. Oh, there we go. Yes, that's what it is. Okay, now I got it. It was 4 choose 2 minus this row. So in that case, I've got this. I can solve this. So we just need to know how many appear below 10,000. Right. And then subtract those out. Well, first let's figure out how many appear. That's how we're going to solve this. We're going to figure out how many of these numbers appear in the first 10,000, and we're going to do it in the next 99,000 and subtract it out. That's how to approach it. Okay, so 10,000. So we have 5 numbers, right? First 10,000, you can have 3, you can have 4, you can have 8, you can have well, we're going to say 10,000. We're not going to say 10,000. We're going to say 9,999. So we're going to have 4 spots, 4 stars, 1, 2, 3, 4, and we're going to say we're going to give it to the 8s here. I'm going to say 4. So this number right here, this is equivalent to 8,888. Okay? So we gave the 4 stars, the 4 placements to the 8. And yeah, so then we're going to say 4 stars, 3 bars. So that's going to be 7, choose 4 for the first 9,999. Okay, and we're going to subtract those out. And that's 35. Because we take out, I'll show you, 7 times 6 times 5 times 4 factorial over 4 factorial, 3 factorial, scratch this, 35. Okay, so there are 35 different ones we can do. We just have to subtract the number 35. Now, by the same principle, the next number, the 9,999, we're going to say this number, highest we can go is 8, 8, 8, 8, 8. So then we're going to say 1, 2, 3, 4, 5, 5. And then we're going to say this is going to be number 4s. This is a number of 3s. It should be 2 bars, though, not 3 bars. Right? It's 2 bars? Yeah, that's I made a mistake there. That 3 does not need an extra bar. So let's roll that back for a minute. We're going to roll this back. We're going to say this is 7. I know I'm on the right track here. 7, choose 3. So, no. I did 7, choose 4. Okay, so that was stars total, and then no, I think that's right. Except it should have been 6, choose the number of bars is, yeah. So it is gonna be 7, choose 2. Not 7 then. It would be 6, choose 2. So we have 1, 2, 3, 4. That's 4. And then we can divide them into 2 bars. Oh, 8. No 4s, no 3s. So that's 6, choose 2. 6, choose 2. And that's going to be 6 times 5 times 4 factorial over 2 factorial, 4 factorial. Make sure. Yeah, 6 times 5 times 4. Yep. And then scratch those. Scratch. So that's 15. There are 15 numbers. And just for the just for convenience sake, we can probably even just add those up. So that's going to be first 10,000. Let's put them in here. 9,000. Yeah, I should be able to just write them out. So 33. The next set would be 88. There should be more than that, though, I think. So this is first 9,999. So 3, 3, 3, 3. We can have 3, 4, 3, 3, 3, 4, 4. There's a lot more than 15. 3, 4, 4, 3. Yeah, there should be a lot more than that. So that means, hold up. So that's 3 4s. And then the same thing will be with the 8s, right? 3 3 3 3, 3 4 3 3, 3 4 4 3, 3 4 4 4, and then we're gonna say 3 3 3 8, 3 3 83, 3 3 43. 344, 3, 3, 4, 4, 4. Okay, so that's going to be 10, 15. And we're going to say 3, 3, 8, 8. And then we're going to say 3, 3. We're going to say 3, 8, 8, 3. And then say 3, 8, 8. About 3, 8, 3, 8. 3, 8, 3, 8. And then there's the 3, 4. And then there's going to be the 4s, and there's going to be the 8s. So that's 1, 2, 3, 4, 5, 10, 15. There's probably close to, let's see here, 5. Should be probably more like 45 or something like that. So let's try this again. At least I'm starting to get a feel for this equation. Okay, so we have, so first 9,999. We are going to have, so we have 4 spots, 2, 3, 4, right? And repetitions allowed, so we can stick the 3s. So our n is just 3, 8, and 4. So that's n is equal to 3. So that looks to me like, so that's going to be, there's 4 spots, and any one of those can have any one of those spots, right? 3, 4, and 8. So that would be, one way is to do stars and bars, the other way would be to say k plus n minus 1 over k. So that would be first, it would be 3 plus 4 minus 1 over 3. Six times 3, I believe, is 15. That it has to be a higher number than that. So if it's yeah, 6 times 3. Wait a minute. 6 times 3 is, I think it's 20 actually. Hold on. Yeah, 6 times 3 is 20. So is that right? Another way is to think of it as stars and bars. Because you can also just have 3 here, right? Or we would have to add the, let's try a star allocation. If we're going to go with 4 spots, 1, 2, 3, 4. So we're going to say, actually, if we go with 3s, we're going to give it 3 spot allocations to the 3. So it would have to be 4 stars, right? 1, 2, 3, 4. And then 2 bars. So we have all 3s, a 4 and an 8. So that's 3,333. So that's again a 6 choose 3. Okay, but that implies that I think we might have to add the lower numbers too. That implies the stars get spread in some way. I don't think we can have a 0 star option. That's the only problem. The lowest number here now we have is 3333. And we need to get our 3-digit numbers. So let's do that. So we're going to say this is going to be 20 plus 999. So now we have 3 choose 2. So in other words, we're still doing, now our K is 2 spots, but we have 3. So that's going to be 6 factorial. So that's going to be 3 factorial over 2 factorial, 3 factorial. What? No, over 1 factorial. 2 factorial, 1 factorial. So that means 3 times 2 divided by 2. So that's 3. So that is true only for the first 10. So that's going to be, I did something wrong here. 1 through 10. 1 through 10, there's only 3 spaces we can do here. The first 999 should be 12 spaces, and that was 4 choose 3, I think. Four choose 3, wasn't that right? Or was it 4 choose 2? It was 12. 4 choose 2, that's what it was. Okay, well, we just have to add a space. So we're going to do 4 choose 2. So 3 choose 2. Okay. 1 through 10 is 3 choose 2, which is equal to 3. 10 through 99 is 4 choose 2. That's going to be 12. We're double counting, so we're going to have to subtract some of these out. They're going to say... Yeah, that's right. That's right. So, except, hold on. 4 choose 2. Let me see here. Where was it? It was 4 choose 2. Yeah. Wait a minute. What if it was... Here we go. The first 99 contained 9. And that's because we had to subtract. So the first was... I got it. I think I understand it. Okay. For the 99... this is we had n plus k minus 1 over k. K is, there's 2 spots, and we had 3. There we go. That's what we're using. I got it. I got it. We're using n plus k minus 1 over k formula, and that's going to give us our answer. So, 3 plus 2... over 2, so that's going to be 4 choose 2, right? This is for 2 spots for first 99. For the 2 spots, for 10 through 99 is 4 choose 2. And that's going to be 12. Wait a minute. Okay. All right, let's do this again. Okay, I've got this. Okay, 33 point. So we're going to say 3, 4, 8. So we know for k is equal to 1 spot. For 1 spot, it's going to be an n is equal to 3. So this is going to be 1 through 9. So that's going to be 3 plus 1 minus 1 over 1. So that's 3 choose 1. So that's 3 spots, okay? Now, k is equal to 2 spots, and that's going to be 9 through 99, okay? And in this case, but, oh, that's 10 through 99. Right, because they have to have 2 spots. And it's still equal to 3, okay? So that's going to be 3 plus 2 minus 1 over 2. So that's going to be 4 choose 2. And that's 24. And I'll show you real quick. So that's 4. A minute. I'll do it right here and I'll erase it. 4 factorial over 2 factorial, 2 factorial. So that's going to be 4 times 3 times 2 times 1 over 2 times 2. Actually, it's 12. 12, not 24, it's 12. See, that's good to check. Check your own work. Yeah, so that's 12. So, so there's an overlap between the first two. There's actually 9 of this one. But we're calling it 12. So then the next one is going to be k is equal to 3 spots and is equal to 3. So that's going to be 3 spots. So that's so okay, I think I got it. So we need to figure out for the 4th spots for 900,999, k is equal to what? Our 3 spots. And k is equal to 4, n is equal to 3. So that's going to be 4 plus 3 minus 1 over 4. K factorial. Is that right? Yep. This is now 900,999. Yes. So that's going to be 6 choose 4. Okay, 6 times 5 times 4 factorial over 4 factorial, 2 factorial. 15. Okay. Hmm. 15. Right. And then for K for 999 was 3 plus 3 minus 1 over 3. There's 5, choose 3, which is 10. Which is 5 factorial over 3 factorial, 2 factorial, which is equal to 5 times 4 times 3 factorial over 3 factorial, 2 factorial, 20, 10. Okay. So I think I have to add all of these up. But I have to be careful how I do it to avoid double counting. Yeah, and then the last one, 9,000 for 5. So 9, 9, 9, 9, 9. We're going to say K is equal to 3. N is equal to 5. So 5 plus 3 minus 1 over 3. So that's going to be 7 choose, wait a minute. 7 choose 3, which is equal to 35. Okay. So there's 35. Between 10,000. Okay. So that's when it uses all of those numbers. I think it's just 35 actually, because we don't need to worry about the numbers that are below 10K. I think it's just 7 choose 3. And it's not counting them because the lowest number here will be 33333. So I think it's this. Let's find out. No, not quite. Okay, well, let me see here. Okay, so no, I didn't answer it correctly. Let me see here. If I had added them up, no, still wouldn't have given me the right answer. Okay, permutations. That's the solution. So basically what we had was first count number of 3s, 1s, and 8s. All right, let me try to work this out. Okay, so basically it is 5 factorial, 3 factorial, 1 factorial, 1 factorial. And that's because if we had, so 3, 3, 4, 3, 3, 3, 4, 8, or any arrangements where it's 3 3s, right? So that's going to be 20. 5 choose 3 is 20. Next, consider 2 3s, 2 4s, and 1. So now we have 5 factorial over 2 factorial, 2 factorial, 1 factorial. Okay. So that's going to be 30. And that's such as 3, 3, 4, 4, 8. Okay. So basically, we just have to do, and the same thing can be done 3 times. Times 3 for each of the numbers. You know, you could have 4, 4, 4, 3, 8, and so forth. So then you end up with 60 and 90, 150. All right, well, that was a hard one. Yeah, we got a lot done, but it was a very hard session. Hopefully you learned something.